Okay, this is a typical battery question where we have some cells connected in a series and parallel combination. We are told that we have 5 cells connected in series per row, which means that S is equal to 5. In addition, we have 4 of these rows connected in parallel, so P is equal to 4. And that gives us a battery bank, if you will, that contains 20 cells. Now, when we try to produce the equivalent circuit shown, we'll start off by saying that the EMF of the battery, or the ET, is equal to S times the EMF of a single cell. And so that gives us 5 multiplied by 1.5 volts for a total EMF 7.5 volts. And so if you refer to the notes for the battery section that are provided for this course, you will find that there is a page which contains a summary of the equations that applies. And if you look there, you will find that for a series parallel combination, the total internal resistance is given as S multiplied by the internal resistance of a single cell divided by P. And so we have 5 multiplied by 0.2 ohms and divided by 4, and that gives us 0.25 ohms as the total internal resistance. And so if we use that information to draw equivalent circuit which represents the battery in question, and we have RT at 0.25 ohms, ET at 7.5 volts, which gives us the terminals of the battery 1 and 2 here. Externally connected to the battery then would be the load 4 ohms as is suggested in the question. Now, so then we typically want to have a look at that equivalent circuit, and we are asked to calculate the current, which we can call IL, and the terminal voltage of the battery, which you might note is equal to the voltage drop produced across the load. Now, here, this is a simple series circuit which contains just 2 resistors in series connected to the source. And so we should be able to say that rules for series circuits tells us the total resistance is equal to the total internal resistance added to the load resistance, which gives us 0.25 ohms plus 4 ohms, or a total resistance of 4.25 ohms. Now, Ohm's law then will allow us to say that the current in the circuit, which we have called IL, is equal to ET divided by RT. We have 7.5 volts divided by 4.25 ohms, and that gives us a circuit current of 1.765 amps. So that's one of the things that we are asked to find. Next, we are asked to calculate the terminal voltage of the battery, which, as we've said, the terminal voltage here is equal to the voltage drop across the load, which we can call VL. And so that means that we can write VT or VT is equal to VL, and by Ohm's law we have IL times RL, 1.765 amps multiplied by 4 ohms. And if we do the math on that one, we can say then that the terminal voltage of the battery is equal to 7.059 volts. Now, remember that we have generally calculated the terminal voltage, or we can calculate the terminal voltage, as the voltage here subtract the voltage here gives us the voltage at the terminals. And we have presented that equation as VT is equal to ET subtract the voltage drop across the internal resistance, where the voltage drop across the internal resistance is equal to the circuit current multiplied by the internal resistance. And therefore, we can say VT is equal to ET subtract IL times RT. And if we do that, we can say 7.5 volts subtract 1.765 amps times 0.25 ohms. Now, the product of the current and internal resistance results in a voltage drop internal to the battery, 0.441 volts. And so that gives us 7.5 volts subtract 0.441 volts, or a terminal voltage of 7.059 volts. So remember, we've calculated that terminal voltage using two different methods, and of course we have found the same answer, 7.06 volts basically, in either case. And so remember that when it comes to circuit analysis, it doesn't matter how we do the calculation. What matters is that we have calculated the potential difference between terminals 1 and 2 here as 7.06 volts.